To continue on with film screen radiography, we're going to get into film processing. For this lecture, the major focus is going to surround the automatic film processor. So we're going to get back into all of the individual tanks, and we're going to talk about all of the individual subcomponents that make up those solutions. So not just the developer as a whole, but the subcomponents in the developer. Not just the fixer, but the subcomponents within the fixer. And then further, we're going to break down the automatic film processor. We're going to talk about all of the individual systems, like the transport system or the replenishment system. So you really get a nice comprehensive sense of what the automatic film processor is all about. To begin, let's really just think about the exposure process. So we're taking our X-ray, and our film is being exposed to that ionizing radiation. The individual image that's in our hands is invisible to the human eye, and as such, it must be processed. There's a couple different methods that are indicated here, either a manual process, which is really old school, or an automatic process. But the whole idea is to make that latent image or that hidden image become that manifest or visible image. For the image to become visible, what must happen is that the silver within the film, it's going to have to change from an ionized state to a neutral state. And when it does this, what happens is that excited silver ions are going to subsequently turn black. So that's going to create those high density areas. And then anywhere that was unexposed on the film, all of that silver is subsequently going to be removed during the processing. So in processing the image, it's not only converted, it certainly is preserved as well. So the overall idea with film processing, nonetheless, is to convert that hidden image into a visible image, or a latent image into that manifest image. The essence of film processing is the same whether it's an automatic process or a manual process. But with a manual process, what happens is that the film is physically moved from one solution to another solution by hands. So during this, of course, it creates some variables. What if you leave in your film in one of the tanks too long? Or what if the temperature becomes much different from one tank to another tank? It's going to create some visual differences. So the probability of error is certainly greater in a manual process than it is within an automatic process. But nonetheless, with a trained individual, this is certainly a method that can be applied effectively. So you look at the list here, and you can see that a lot of the elements that you're familiar with within the automatic process are still within the manual process. So again, the essence is relatively the same. Where the start is a little bit different is something called a wetting agent. It is optional, but what essentially happens is that this is a chemical designed to loosen up the emulsion on the film. So essentially the solution of the developer can reach the emulsion uniformly. The other aspect is the wetting agent also reduces development time. So essentially you're going to dip your film into the wetting agent 15 seconds, and this is really going to help accelerate that process. Next up, it's going to go into the developer. It is considered the most important processing step because this is where it all happens. This is where the conversion of latent image to manifest image officially takes place. It is going to take about 3 to 5 minutes within this developer solution to process or allow this development process to take place. It'd be 3 minutes if it's a little warmer, 5 minutes if it's a little cooler. So the amount of time it's in the developer is certainly going to be dependent on the temperature of that developer. Next up is going to be the stop bath. Stop bath essentially is a water rinse, and it stops the development process, removes any excess developer, and this process can take 30 seconds if you use just water as being your stop bath agent, or it could be accelerated a little bit to 5 to 10 seconds if you mix acetic acid with that water. So another kind of variable that's a little bit different than the automatic process. After this, it goes into the fixer tank. And the fixer is designed to remove unexposed silver halide crystals from the emulsion. So this is going to, on finished product, is going to create all of those very low densities or clear areas on those radiographs. But the fixer does one more thing, and it functions to harden the emulsion for permanent storage. So while the emulsion was being softened early on, it's being hardened back up within that fixer. Fixer generally takes about 10 total minutes, but it is dependent on cleaning time and hardening time. So cleaning time would be the removal of those silver. Hardening time is, preparing it for essentially archival quality. Next is wash. So the wash aspect of things is designed to prevent something called hyporetention. And hyporetention is this white powdery substance on the film itself. So it's going to prevent this, and it does this, preventing by removing the excess fixer from the film. Process can take a while. It can take anywhere, it can take really up to about 20 minutes to complete. Final aspect is the drying phase, and this is going to prepare the film for viewing. This can be done by hanging it in a room for an hour, or it can be accelerated much quicker if you use like an electric dryer, and that process could take between a minute. So between a minute and an hour, of course, there's a large amount of time differences there, but the overall idea is that the drying should allow for that viewing of that finished radiograph to take place. Now, when you compare the automatic process and the manual process, I think there are some very clear pros and cons that are present. The manual process is going to take longer, and it has a greater probability of inducing an error. But what's great about the manual process is that it does have lower costs and lower maintenance. So, and vice versa, what's good about the automatic process, faster processing times, less variability, but it is certainly a more expensive system. So, take the good with the bad. With the automatic process, some of those steps that we previously mentioned, like the wetting agent and the stop bath, they're no longer going to be present in the automatic process. Kind of how the automatic processor works is that the film will always travel from developer to fixer to wash, regardless of the manufacturer. But the overall makeup of the film processor, kind of its design, will be manufacturer or vendor dependent. So you can see that they're pictured here, two different pictures. But you can follow basically the film from the entrance rack and in. It's going to go into the developer through the roller system, cross over into the fixer, jump into the wash, jump into the dry. Down here you can see just a little bit different variation of the process for kind of how the film travels through. This process, the film is going to come in. It's going to drop all the way down to the bottom of the developer tank, come back up, cross over, jump into the bottom of the fixer tank, come back up and cross over into the wash, and then subsequently cross back over into the dry. So the order itself is certainly important. So developer, fixer, wash, dry are going to be the basic primary steps of the processing of any radiograph. Now, to get into the processor chemistry, we're going to start with the developer, largely because the developer is the first tank, but it also is considered to be the most important step. Now, the developer can come in a variety of different ways. It can come ready or pre-mixed, or it can come in concentrate form. The pre-mixed form is considered to be much easier for obvious reasons. It's ready to go, but it is more expensive. The concentrate form is cheaper, less convenient. It's typically a 3-part kit, must be mixed with water, and as such, it has to be mixed appropriately. So that's something to kind of keep in mind when you're evaluating, different developers, different options. But the whole function of the developer is to make that radiograph visible. And the agents that are going to allow that to take place are called developing agents or reducing agents, and they're listed here. Phenidone and hydroquinone. Phenidone is considered to produce the lighter shades of gray, so any OD or optical density under 1.2. And hydroquinone is slower acting, but responsible for producing more of the dark shades, the blacks, optical densities above 1.2. What's really cool about these two chemicals is they do have synergistic properties, which just means that the two agents together have a much greater effect than the two do individually, and that's largely what this graph is trying to indicate. So when you look at this, what it's basically saying is that development time is increasing, so the two together have a much faster development time because they have a much faster effect than the one individually and the other individually. And this is kind of basically those being retrofitted on top of each other. So to truly say that, yes, this has a faster development time than this one, being able to produce the same optical densities takes less time. So pretty cool stuff. Now, there are more agents than simply the reducing agents that we mentioned. There are preservatives. And some of the preservatives, one of the most common preservatives out there is sodium sulfite. So the whole idea of the preservative within the developer is it's supposed to prevent oxidation from taking place. But another little chemical is the activator or the accelerator, and the whole idea of this is to help increase that softening and swelling of that emulsion so those developer reducing agents can really get in there. But it also helps to maintain a relatively high pH balance for the developer. And the main agent for that is sodium carbonate. So other additional components within the developer, restrainers, are possible, and these are designed to allow the developer to only function or focus on the exposed silver. Major agent for that is going to be potassium bromide. Hardeners are going to be present, and the idea is that yes, the developer is making the emulsion soft, but we don't want it so soft that it becomes sticky, it sticks to the rollers, and it kind of comes off of the film. So there is going to be a slight hardener that's going to be present as well. Glutaraldehyde is that hardener. Now, to finalize the developer components, there is going to be a solvent present. So without the solvent, which is typically water, there would just be a bunch of chemicals, and there wouldn't be a solution possible. So you're adding water to these chemicals to create a solution that becomes the developer. Final aspect is that there may be a sequestering agent specifically if your developer comes from concentrate. So in order to overcome the purities from the water that you're using, an agent called EDTA or editate may be added to the developer to keep it nice and fresh. So to touch a little more on the developer beyond those chemistry aspects of things is that the developer is certainly temperature dependent. And it's said that optimal developer temperature is between 68 and 72 degrees Fahrenheit. This is more for a manual process. The automatic processor is going to be much higher, so 85 to 105 degrees Fahrenheit. The idea is that this is going to accelerate the process. So as I mentioned before, the warmer the developer solution is going to be, the more quickly it can process through that. Immersion time is another factor to consider though. So the greater the length of time in the solution, the greater the optical density, or the more black it's going to be. So you have to be able to control how long it's immersed in the temperature. So it's got to be nice and controlled process that the temperature has to match the time, or we're going to have differing appearances in optical densities. Solution concentration for the developer needs to be between 1.07 and 1.10. The additional points after the decimal are going to be important, so make sure you do know those. Solution concentrate essentially refers to the percentage of water versus chemicals. It can be reported or measured in specific gravity. And the instrument that's used is going to be something called a hydrometer, so make sure you do know that information as well. Solution pH is that the developer acts as more of an alkaline or a base. It has a higher pH, so pH between 10 and 11.5. And finally, exhaustion/replenishment is that a certain volume is removed by the film's emulsion with each piece that's going to be processed. So you can't just use the same developer, or the developer levels are going to go down. So developer, as film goes in, is going to need replenished as well. So a nice example here to kind of reiterate the idea is that the developer is temperature related. So with all things considered equal, you can see from this graphic saying that immersion time is identical for each of these. How does the temperature affect optical density? Well, clearly when you look at the graphic, you can see that this has the highest optical densities, and that makes sense because it's the highest temperature. So you can see visually the changes that are taking place from 85 degrees Fahrenheit to 90 to 95 to that 100 degrees Fahrenheit. So just kind of keep that in mind, that developer temperature certainly will have a visual effect on the quality of the radiograph. Now, to look at this in a different way, assuming that the temperature is stable, nice and stable, and in this particular graphic, it's at 68 degrees Fahrenheit, what's going to happen if we adjust our immersion time? Well, of course, if our film is in the developer longer, it's going to become more developed. So what that's going to mean is that it's going to have a higher optical density, so not something that we necessarily want. So you can see the visual changes that take place between 2 minutes, 4 minutes, 6 minutes, and 8 minutes, assuming that it has this constant 68 degrees Fahrenheit in temperature. So these are just kind of some ideas to kind of keep in mind, so that developing temperature and immersion time are very, very important because they change the appearance. So if we have a nice, strong quality control program, we can minimize these appearance changes, and then we can just go back and say, hey, your film is dark. It must be because you use too much mass. But as many variables as we can take away, certainly the better. So this is one thing to keep in mind. Just like the developer had a series of agents associated with it, the fixer is the same. It doesn't use the same agents, but it has a lot of agents that are associated with it. So do recall the function of the fixer as indicated here, so that's important. But also understand that, like the developer, it also can come in multiple different forms. So it can come in a ready or pre-mixed form. Certainly it's going to be easier, ready to go, but it's going to be more expensive as such. It could also come in a concentrate form. This is going to be cheaper, less convenient in that it's going to have a two-part kit that must be mixed with water. The water is going to have to be mixed appropriately in the correct amount with the fixer. One very, very, very important thing that I want you to write down is that fixer should always be mixed before the developer, largely because inadvertent splashing of the fixer can contaminate that developer, and it will have a visual effect, so not something that you want. It's largely because the pHs of the fixer and the developer are so very different, so do kind of note that. There can be a test conducted to make sure that your fixer is functioning appropriately. So one of its functions is to remove those unexposed or underexposed silver halides. So there is a fixer clearing test, and essentially what this is that you dip the film into fixer, and it should be a green film or a never used, never exposed film. And the idea is that it should be clear within 10 seconds at room temperature, or within 7 seconds if your fixer temperature is at 90 degrees Fahrenheit. So that is a test that needs to be conducted to make sure, yes, your fixer is doing what it's intended to do. Yes, you're going to waste a nice clean piece of film, but yes, we need to make sure that the fixer is functioning appropriately. So the most important agent of the fixer is going to be the fixing agent. It also could be called the clearing agent or hypo, so be able to associate those individual like names. So it's going to clear that film off, and that agent that is going to be most important is going to be ammonium thiosulfate. So make sure you do note that. It could also be sodium thiosulfate as well, so it is an or, not an and. So some additional agents that are within the fixer, one is that there's going to be a preservative, typically sodium sulfite will be used, and this is going to make sure that the fixer can be utilized as long as possible. There's going to be another very important agent called a hardening agent or a tanning agent, and one of the major functions of the fixer is to re-harden that emulsion, and that's what this agent is going to function to do. So you can see some of those agents listed there. Potassium alum is going to be one of the most commonly utilized agents within the agents as a hardening agent. There's going to be an acidifier, activator, or buffer, and what this is going to function to do is neutralize any developer that may be left on that film as it goes from that developing tank to the fixing tank. It helps to maintain that acid-like environment or low pH environment. That pH is going to be anywhere between 4 and 4.5 for the fixer. So pH is much different, again, between the developer and the fixer. Fixer should always be mixed first. And then you can see what these agents are. Acetic acid is one of the primary acidifiers of the fixing. There's going to be a sequestering agent, and this is going to essentially help also when developer kind of comes into the fixing tank. It's going to prevent the formation of materials, one of which that can form is aluminum hydroxide. So don't want it, so in order to prevent that, some sequestering agents are added to the fixing materials. Now again, there's going to be a solvent, and just like there was in the developer, and it's the same agent, it's water. So you're taking all of those chemicals and you're making them into a solution. Keep in mind that the specific gravity, as measured by a hydrometer, but for Fixer is going to be 1.077 to 1.11. And make sure you do note the numbers after that decimal point because they are slightly different between Fixer and developer. So if you cannot recall anything about the pH scale and kind of understanding the differences between acids and base, this graphic should give you a good idea of what that indicates. This line at 7 is considered to be neutral, so neither an acid or a base, but a neutral type of solution. And anything between 0 and 7 is an acid, and anything between 7 and 14 is an alkaline. Of course, the higher the number, the stronger the alkali. Also could be called a base, and then the lower the number, the stronger the acid. And so you can kind of see where the developer solution and the Fixer solution fit in comparison to some other common things like blood, rainwater, grapefruit juice, stomach acid, accordingly. So it's not Fixer isn't as acidic as stomach acid, but nonetheless it still is an acidic based material according to the pH scale. So the wash aspect of things is super important in order to maximize archival quality of the film. The whole idea is that we're trying to remove any excessive Fixer from the film surface because this is going to cause, excessive Fixer will cause hyporetention. It'll cause that white powdery residue in the short term, so it'll have that white effect to it. But long term, it's also going to create this brown type of stain on the radiograph, so hence degrading the archival quality of the images, not something that you want. So you can see the different tanks here nonetheless associated with this automatic process. So when we pay attention to where the film is coming through, so kind of the entrance area, film's going to travel into the developer. Okay, it's going to be developed. It's going to go into the Fixer. All that excess silver that wasn't exposed is going to be removed. It's going to go into the wash, and all of that Fixer, that excess Fixer from its surface is all going to be removed out. And then it's going to dry and prepare, and we'll get to the drying phase next, but you can kind of see that same idea. Looking at this processor from kind of a bird's eye view, you can see the same type of idea, just more of the real graphics. So you got your developer tank here, you have your Fixer tank here, you have your wash here, and then you have your dry there accordingly. In order to verify that the wash tank is functioning appropriately, a hyporetention test is going to need to be performed. These are going to be done at least every 6 months, and how it's done is you're going to drop some test solution onto the film, and you're going to see how much brown stain forms, and the brown stain would be indicative of hyporetention or retained Fixer still with on that film. So ANSI has a standard for this. So ANSI is the American National Standards Institute. It's a nonprofit organization. They have all kinds of standards out there, not just those related to medicine. But it's 2 microgram per centimeter squared for standard radiologic film and 5 micrograms per centimeter squared for mammographic film. So a little bit different, but I would be familiar at least with those numbers. So getting a little bit more into this, specific gravity is indicated here for water, and it does need to, of course, be 1.0. But there's also an indicated pH, so different characteristics are in place here, but one big and important idea to understand is that the temperature needs to be 5 degrees less than the developer temperature, and all of these temperatures that are indicated here, they're all going to be set by the manufacturers. So whatever the manufacturer says is the developer temperature, typically 5 degrees less than that developer is going to be what that wash needs to be. Now, since we are dealing with chemicals here, standards must be posted for all employees to see, and largely because processing chemicals are considered health hazards. So eye stations have to also be available, but why these regulations are in place is they're OSHA regulated, so employees must be made aware that these could be potentially dangerous. But also, the chemicals have to be indicated on an MSDS, so Material Safety Data Sheet, for these purposes. There are different levels here. You can see obviously they increase from 1 to 4, 4 being the most hazardous level. Developer is perhaps the most hazardous of the processing solutions, considered to be dangerous to the eyes and hazardous to the skin. Fixer is also considered to be dangerous to both of those areas, as well as a potential respiratory irritant. So, big stuff. And so employees need to be aware of this. We need to operate appropriately within our dark rooms or within the areas that contain these individual chemicals. So how we protect ourselves is with the use of PPE. So OSHA requires this to take place, and simply it's designed not to be an additional burden to you, but to actually protect you and your coworkers. So it is mandated that when working with processing chemicals, you should be wearing eyewear. Rubber gloves and gowns need to be provided, especially if you're mixing those chemicals or transferring chemicals. And if at any time those chemicals do splash on your skin, you need to wash them and wash them off immediately. And that's another reason why eye stations are going to be required. Finally, the EPA also has guidelines in place that kind of regulate film processing, one of which is that the amount of developer that one uses does have to be reported out. And also, if you plan to carry film, you must have a special permit to be able to carry and transport that film. What I consider to be the major big call out as far as the EPA is concerned is the amount of silver that's flushed down the drains and returns back to the municipals. That amount can be no more than 5 parts per million. Certain silver recovery systems are going to be in place, and one of the reasons why they are in place is to indeed comply with EPA standards and law. Now, this concludes part 1 of film processing, and at this point your big takeaways is to really have a firm understanding of what's going on with the developer and what's going on with the fixer.